title and I was trying to
internalize it, yeah.
So it's about renormalization, and there are rotational attractors in two-dimensional dissipative systems. There you go.
Thank you, Marka. Is this live now? Good stuff. Okay, so first of all, I would like to thank not just the organizers, but everybody who made my years of grad school and consecutive visits to the Institute such a wonderful mathematical experience. And I came here in '92. I'm not quite as old as the IMS. I'm only 23. But it's been great. Like Adam and others have said, home away from home. All right. Like Marcus said, it's a long title, and the story is going to be kind of involved, but I hope to get you through it, or at least through most of it, in an hour. Just before I do it, I wanted to, this reference that I mentioned to you, well, I just wanted to mention Dima Khmelov explicitly. That he was a student of Kostya Hnon and a postdoc of mine, and sadly he died very young. And just wanted to explicitly mention his contribution to the theory that Wellington was talking about. Him and I proved way back when, about 10 years ago, the similar theorem to what Wellington was saying in the analytic class for the general rotation numbers. Okay, so let me tell you the story, and before I do, I would like to give you several motivating questions, or several motivating examples. In fact, I would like to give you two motivating examples. So let's start with the first one. So question one. This one has to do with semi-Siegel points of dissipative and R automorphisms of C2. So we'll look at a dissipative and R. We'll have f of x, y, x and y are complex variables. Fc of x plus y in the first coordinate, bx in the second, and b is very small. This map is very dissipative. So you should think of this, or we think of this as a very small perturbation of a one-dimensional map of the quadratic polynomial f sub c of x. This is a polynomial automorphism of C2, and the question has to do with semi-Siegel points. So let's say this has a fixed point. I don't know, call it P. So f of P is P. And if you linearize at P, then one of the eigenvalues is an irrational rotation on the circle. Okay, so we could fix it to be something nice. Let's say it's the rotation by everybody's favorite angle, by the golden mean. Right? So this would have eigenvalues. Once you linearize, then eigenvalues would be lambda 1, which is this large enough, by the way? Can you see this in the back? Okay, so e to the 2 pi I theta, say, star, where theta star is square root of 5. Usually you write minus 1 over 2. It doesn't matter, of course, if you write plus or minus 1. This way you get a number between 0 and 1, which expands into a continued fraction with all ones. Right? If you don't know why this is nice, shame on you. Right. Okay, and lambda 2 then something small. And you know what? I'll abbreviate such continued fractions in the future like this to save the molecules of chalk. Okay, so such a thing just like in the one-dimensional case, is linearizable. So by the classical theory. So Eric Bedford, for some reason, every time I ask him where this appeared first, always gives me an elusive answer. So, and I'm not an expert in multivariable complex dynamics, so I just don't know. So, so this linearizes. So there exists a linearization. So there exists a map phi from, where do I want to put C? In the first coordinate or in the second? Doesn't matter. Let's say I put it in the first. From C times the unit disk into C2. This is a biholomorphism onto the image. On to the image, which linearizes the map. So phi conjugates f to the linear map, lambda 1x, lambda 2y, and moreover has the property that this is maximal. So it's maximal in the sense that the image is maximal. Okay? So, so this will be maximal. So it's a maximal linearization. So if you look at the image of this, that's a maximal linearization domain. That's your analog of the Siegel disk in one variable. And of course, in this domains, there is the dynamics is very simple, right? It's a rotation in x and contraction in y. So everything converges really fast to the invariant disk. And this is what I would call the Siegel disk. I know that the strange people who do C2 dynamics for some reason call the whole cylinder the Siegel disk. I don't know why they do it. So the Siegel disk for me, delta, will simply be the image of 0 times d by phi. That's a biholomorphically embedded disk in C2, which is the attractor on this basin. So the question one is, what can you say about the boundary of this? Okay, so I'll be specific. I'll ask whether is the boundary a circle? Okay? Topological circle. All right, so I don't know who this question belongs to, probably folklore to some extent. There's a clear analogy with similar questions in one dimension. So let me ask the second motivating question, and that one I know who the author is. It was stated.
What is rotating and what is contracting?
The second coordinate should be rotating.
Huh?
First the
Lambda 2, lambda 1 is the one on the other way.
Oh, yeah. You absolutely. Oh, yeah, yes. Horrible. Of course, the right thing to do is exchange these, right? Yeah. But the easy thing to do is interchange these, right? So we'll do the right thing. Because otherwise, it would be just wrong. Yes, I know. I was just getting started. I know. You know, essentially every theorem is correct if you change a few words around here and there. This is no exception. Okay, we happy? Good. So question 2, I actually know who asked it. This was asked by Enrique Pujals. A little less, I heard it from him a little less than 2 years ago.
The circle, like the circle.
Topological circle is homeomorphic to a circle. How's that?
The expression is the same disk. I'm just looking for.
Let's just quickly move on. So, if you don't mind. So the second motivating question will be a little bit more general and therefore a little bit more vague. Don't worry about that. The theorems will not be vague. Okay? So, second question is not about complex analytic maps. It's about real analytic maps. So we're working in R2 rather than C2. In fact, we'll be working in a cylinder. So suppose you have F or in an annulus. Let's say an annulus. So you have an annulus, just a round annulus, your favorite round annulus, and you have a map from A to A. And let's say this map is dissipative, again, as before. So let it be, you know, a diffeo onto the image, could be a real analytic, as I said. Right, should I write this? C omega diffeo onto image. And dissipative, so the Jacobian is very small. And let's imagine that, okay, so this has an attractor sort of in the most naive sense of the word. The attractor lambda, which is just the intersection of, so this is the intersection of the images, forward images of A. Okay? We would like to put ourselves in a similar situation to the previous example. So in the previous example, we had a small perturbation of a quadratic polynomial with a Siegel disk. Here we want to see a small perturbation of a circle map. Right? So let's assume that F is a small perturbation of a circle map. Okay, so there it's almost real symmetric. And that lambda is minimal. Okay, so orbits are dense. So then you can also ask, is lambda, this is not yet question 2, okay? This is a preliminary question to question 2. You could ask, is lambda a circle? Of course, it's easy to cook up examples where lambda would be a circle. In fact, it's easy to cook up examples in which lambda would be a smooth circle. Right? Think of a picture of a normally hyperbolic smooth curve. Everything converges to it, and you have an irrational rotation on this curve. So what Enrique asked is, are there examples? So, okay, so not interesting. Are there cases when lambda is a critical circle? So to understand this question precisely, so critical, we understand what it is, right? This has to be on the boundary of the smooth conjugacy case. So to understand this more precisely, let's look at a specific family of examples. Like here we looked at Hénon. Let's look at everybody's favorite family of circle maps and then perturb it. So I'll look at Arnold's family. So f of A omega of x is x minus a over 2 pi sine 2 pi x plus omega. Okay, this maps the real line to the real line, commutes with the unit translation, therefore gives us a well-defined circle map for A equal to 1, this would be a critical circle map. It will have critical points, and less than 1, it would be a diffeo. Okay? And then we'll embed this into a family of small perturbations, same way as with Hnon. So we'll consider family fxy is equal to fa omega of x plus y. In the second coordinate, I just have to put something small and one periodic. So Enrique, I actually looked in his slides. Enrique put b times f of x minus x plus y. So this is small and one periodic. So this gives you a small, so b again is very small. So this gives you a small perturbation of a circle map.
So you need the y in the second coordinate to make it periodic or what?
Huh?
The y in the second coordinate, and you...
Oh, this? Why here to make periodic? Oh, no, no, why here to because it should be here. X here to make it periodic in X.
Probably gives it constant Jacobian.
Probably does. Okay. So the picture then you should look at is the following. So let's imagine that in this family we fixed the rotation number. Let's say we fixed the rotation number ρ equal to the golden mean. Ρ is, no, sorry, what should I write? I used to call it theta or ρ? Ρ. Yeah, so ρ star. So this would be the ρ star plane. Of course, there is no reason to think of this as a plane. There will be a reason to think of this as a plane in the end of this talk. But for the moment, think of this as a plane. Okay? So somewhere here is, so this is B. This is the B axis. Okay? And this is A omega. So somewhere here is A equal to 1, omega equal to whatever it's supposed to be. This is a critical circle map. And what you should think of is that somewhere here, there's a region in which the circle, there is an attractor, which is a circle with an irrational rotation number, and the circle is smooth. Okay? And then somewhere here, there is a curve on which the circle is critical. So it breaks if you go through the curve. Okay? So that's the picture that Enrique asked about. So of course, you would, the real question is that you would expect to see such a thing typically. Now, oops. We'll get to these two in a little while. Okay, good. So
Open set.
we'll see. There'll be a theorem.
Okay.
There'll be a theorem. So we'll see exactly what to expect. We'll see what's supposed to be smooth.
You did a search when you did that you would expect there to be an open set of values where there was a smooth circle with rotation number exactly the way the golden mean. At least I thought I heard you say that.
Yes. Something like that. It's not really, I'm not really after that set. I'm after this curve. Okay?
You can use a B in order to compensate.
Yes. B and omega in order to. Exactly. Sort of assuming that this is normally hyperbolic and that's stable and the rotation number gives you a codimension 1 condition, there is enough dimension here to have an open set.
Okay, you have an extra parameter.
Okay? Yeah, that's right. So this is a 3-parameter family that you're playing with, so there should be enough freedom here. Okay. So I should mention that there is, at least at that point, there was only one theorem in this direction, and that was due to Enrique himself and Coxard and Korepetsky, which said that just under the general assumptions, F restricted to lambda is semi-conjugate to a rotation. So let's make the question a little bit more precise, my question 2. So would we in a typical family like this, would we see examples in which lambda is a circle and the conjugacy is not smooth. Okay? So that's question 2. So you state it like this. It's a clear parallel with the first example, right? Okay, so for those who know, both of these are renormalization type questions. For those who don't know, don't worry about it. That's what I'm going to tell you about. So these are renormalization type questions. Okay, now you know too. So let's talk about renormalization next. And it's great that Wellington already had the chance to talk about renormalization of critical circle maps. I'm going to be repeating some of what he said, and it's good because it gives you a chance to understand these things better if you see them for the first time. By the way, can you see what's written on this board, or is it blocked by this thing? Yeah, sorry, multiple choice. Can you see what's written on this board? No. Marco cannot see, sorry. I won't go that far. We keep that. That's okay, end of discussion. Marco cannot see. No. Look, guys, I respect all of you equally. But Marco I respect more because when I run out of time, he is the guy who is going to keep. Okay? Sorry. Won't be using that side. Try to beat it out of myself every day. Unsuccessfully so far, but it's early going. So, okay. So let's talk about renormalization, okay? I'll talk about it in both contexts, both Siegel disks and circle maps, but it will be easier for me to start with circle maps for obvious reasons. A real one-dimensional picture is easier than a complex one-dimensional picture. And then we'll get to the complex, okay? So let's start with renormalization of critical circle maps. Okay, so the critical circle map is this guy here, okay? The one-dimensional map, Arnold map, for which A is 1. So that guy will have cubic critical points at all integers, so when you project on the circle, it will have a cubic critical point at 0. Okay, so for simplicity, although this generalizes to some crazy generality, let's not do that. And let's only look at critical circle maps which have a single critical point, and it's always cubic, and it's always at 0. Okay, so this is a map of the circle. Circle is R mod Z. Map of the circle. Smooth, let's say at least C3, and one critical point at 0 and of cubic type. So single critical point at x equal to 0 of cubic type. Okay, so what is renormalization in our business? Renormalization in our business is a rescaled first return map. You know, I started thinking about my talk, and I started to feel that this is about me. I'm like that Feigenbaum polynomial critical point. You start somewhere, then you go away, you do something interesting, you come back. You start, and you keep coming back, and it's somehow it's a scary thing. So here we are with the subject again. So, okay, so here's my 0. This is my circle. I draw it straight because it's flat. It's R mod Z. And I have to look at the first return map. It's entirely irrelevant where you take the first return map, as long as you are consistent. So historically, the choice that has been made by Feigenbaum, Kadanoff, Schenker, and Ostlund, Rand, Setna, and Sija, and then later by Lanford and so on, the choice is the following. You take your rotation number, which let's say is always irrational. You expand this into a continued fraction with positive terms. You take the convergence of this continued fraction. The denominators Qn will be, of course, closest return times for any point on the circle, in particular for 0. And you take an interval between the two consecutive ones to look at the first return map. And I'm sure you've all seen this. Well, look, you saw this picture an hour ago. But it's worthwhile to dwell on it for a bit, because it's important. So here's the picture. This is Fqn of 0, and this is Fqn plus 1 of 0. Incidentally, they happen on the opposite sides of 0. And you look at the first return map of this interval. And it's trivial to, well, it's elementary to see that this first return map is given by iterate Fqn plus 1 on the left, on the right, I'm sorry, and Fqn on the left. Right, so the pink interval shifts over like so. The blue interval shifts over like so, right? These are orientation preserving diffeos, so you should just think of this thing as a translation of some sort. You only need to see where 0 goes to see this picture. Under pink, 0 goes here. So the whole thing shifts to the left. And under blue, 0 goes here. So the whole thing shifts to the right. And incidentally, this is the same point. Right? So, okay, and we're good. We just need to rescale. What does it mean that we need to rescale this? We need to get back to a circle map out of this, right? It's easy. What do you do? You can interpret the pink as the circle, and you glue the ends with the blue. Well, it's not good to glue with the blue at 0, because 0 is a critical point. Just step to the left like it's here. And use this as a glue-in. Right? So you glue the ends like this, and you get yourself a circle, and you'll get a perfectly well-defined circle map out of this. Right? It will be well-defined. It's easy to check. Wrong. What's the problem? Valentin already mentioned this, and it's worthwhile to mention this again. The problem is the following. How smooth is your glue-in? Same smoothness as F. At best analytic, if F was analytic. But it's not affine. Circle, the circle, is R mod Z. To recover the circle, you need an affine chart identifying these ends. And you don't have it. Okay, so you don't recover a circle map. What you do recover is a conjugacy class of circle maps. And the map will depend on the choice of identification of your smooth circle. So you get a manifold out of this, right? You get a manifold M. And this manifold M, which is this thing glued, is isomorphic to a circle, but not equal to a circle. It's isomorphic, and the isomorphism is in the same smoothness class as F. So you have a map here. Call it G. G. from M to M. But it doesn't give you a circle map. To find the circle map, you need to take an identification here. So what it gives you is a conjugacy class, and that's bad. Yes?
By the way, in order to be complete, you need not only grouping and rescaling, you need also renaming. And what you just said, you said it perfectly well. Because that's what you did in normalization. The new packet of spin, you call the new spin. Here we see that.
Okay, so I'll rename it twice during this talk. Twice more during this talk. So the first renaming coming up in 5 minutes. So don't touch that remote. Okay, so so the solution is don't glue, right? And that was the solution that was worked out by people, you know, since time was time, since before I was at the institute. So, and the solution is don't glue. So enlarge, so don't look at circle maps. These are bad. You can't define renormalization action on these, and work with pairs of maps of the interval. So this is the formalism of commuting pairs or critical commuting pairs, however you like to call them. You know what's going to happen next, right? So, commuting pairs. It's the same picture, except now you have pairs of interval maps rather than a single map. Everything else looks exactly the same, right? So you have a pink, you have a blue, and the blue goes over like this, and the pink goes over like that. Oops. And what do we mean by commutation? So I'll call this pair zeta, and the maps would be eta and psi. And I don't remember in which order I labeled them, so just eta and psi, like that. So 0 would be a critical point. What does that mean? That, well, I mean, these are interval maps, but I want to talk about this as a critical point. It's on the boundary, so I want them to have extensions to a neighborhood of 0. And I want them to commute, and that's important, because if they don't, bad things happen. Well, for one, it becomes kind of hard to iterate. Okay? That's a very large class. It's a lot larger, if you think about it, than the class of critical circle maps. You basically squared it. Think about it this way. Let's say your smoothness is C3, okay? The lowest possible smoothness. So here you have one map. Here you have 2 plus a commutation condition, but the C3 commutation condition at one point, I mean, their domains intersect at one point. It's not worth very much. It just says that you have a C3 smooth extension for each of these maps which commute. So it gives you finitely many conditions on the first 3 Taylor coefficients at 2 points for each of the maps. So not very much. So we enlarged our class enormously. But now everything goes swimmingly, right? Now everything is great. This, of course, corresponds to a conjugacy class of critical circle maps. You can renormalize in the same way. I don't want to draw this picture again. Blah, blah, blah. And renormalization is now just, after you take the first return map, you just rescale. These are interval maps, so rescaling is easy. You just always say you put this at 0, and you always make this point 1. So to renormalize here, I just have to compose with the linear map. This goes to 0, this goes to 1. Boom, done. Okay? Easy. And that's where the theory lived. Okay. Now, I don't want to talk about the history of the subject. It's long, and there are a lot of references. Let me maybe, if you want to have some sort of a survey, let me refer you to my year 2000 paper in which there is an introduction which tries to give a bird's eye overview of this. Okay, so now let's see. What do we want from renormalization? We want to prove universality, which is renormalization hyperbolicity, right? As Charles, who is one of the founders of the subject, knows very well. So what do we need to do that? So what do we want to prove? We want to prove something like this. We want to prove that, let's say, if we fix the rotation number to be rho star, so rho is equal to rho star, there is a Banach space, this is a Banach manifold, okay, of maps, of pairs, in which there is a hyperbolic fixed point, and this point has a single unstable direction. That's the rotation number. And this is the stable manifold, and the stable manifold consists of all pairs for which rho is equal to rho star. That's the picture we're after, right? So here you have convergence. Here you have a single unstable direction. That's what numerical experiments tell you. Why do I want this? Perhaps it's time to relate this with the motivating questions, right? Marco, I started 15 minutes late, right? So I have 15 extra minutes, is that correct? Oh, and I was so nice to you. Okay, so of course if you followed the development of the subject in the last little while, you know. So this kind of approach has been done for unimodal renormalizations, for things like the Feigenbaum renormalization fixed point, and this is the work of Misha, Marco, and Andre, and then Misha and Marco, and so on. So you could take the one-dimensional renormalization fixed point and enlarge your space to include dissipative two-dimensional maps. And then this picture will live in the spaces that we're interested in. Well, let's first talk about getting this picture. Okay? So there is, what do we need to get a picture like this? To talk about hyperbolicity. Well, I need a lot of things, but what do we need? And what is the basics? I mean, the basic thing is we want to talk about hyperbolicity of a fixed point or of renormalization horseshoe. So we want to talk about the differentiable structure for the renormalization operator. So we need a Banach manifold of pairs. So what do we need? So we need a Banach manifold in which R acts, right? Banach manifold invariant under R. Just in case you knew, renormalization is always denoted by R.
Sometimes by God.
Yes, you're right. You're right. Okay, you are right. And B, we need R to be smooth, at least C1. So need R to be smooth. And this is where we have to pay for this convenience, for not gluing the circle. And here's how. Okay, so what kind of smoothness can we impose on our pairs?
Well, it depends.
So let's do it. So
Depends what you're asking.
yeah. So it wasn't a question. It was, I was just warming up. Rhetorical. Thank you. Yes. Yeah. Yeah. So, right. So we can do two things. Let's first try finite smoothness. Let's say we try CR. Okay. You got a perfectly beautiful. Where's my perfectly beautiful Banach manifold? I mean, it's essentially CR squared. So it's easy to impose a Banach norm on CR, right? You just take sup norms for the derivatives. First R plus 1. Well, starting from zeros. And then, as I said, the condition of commutation is a very mild condition. It's a finite number of conditions and a finite number of Taylor coefficients at finite number of points. So you can prove, I mean, it's not completely trivial, but it's an exercise. You could prove that you get a Banach manifold. You run into a problem with B. So this is an exercise for graduate students in the audience, if you haven't done it ever. Composition is not a smooth map from CR to CR. It's a smooth map from CR to CR minus 1. And renormalization, of course, involves composition. It's a first return map. And this is bad because you lose smooth, R is not smooth anymore. Okay, so finite smoothness doesn't work. Let's try infinite smoothness. Okay, I'm not even going to talk about C infinity. It's just a horrible, horrible space. So, never mind. You don't talk about these things in polite company. So, let's talk about analytic maps, okay? What's the problem there? Composition is perfectly nice. It's analytic. Better than smooth. The problem is the commutation condition. Instead of being a finite codimension condition in your Cartesian product of two Banach spaces, it becomes this horrible infinite codimension condition because, of course, if they commute, if your maps are analytic, you don't have any freedom anymore in how you extend them. I mean, they extend however they extend, and they either commute or they don't. And I don't know how to impose a Banach space structure with this commutation condition. It's a bad condition to work with. So the solution which I came up with a long time ago, but less than 25 years, was the following, and I'll just draw it. This is what I called, so renaming, right? So this is what I called cylinder renormalization. And cylinder renormalization is the following thing. You complement that picture. So you work with analytic maps. So you take your analytic F. You look at this unfortunate picture in which you cannot glue. So this is FQN. This is 0. FQN of 0. And you don't know how to glue these ends to get a circle. So you assume that this thing, it's real symmetric, that this iterate FQN has a repellent fixed point above the circle. Of course, by symmetry, it will also have one below. And that you can connect them by a curve whose image under FQN translates over, well, has to be closer to the end, translates over like this. So you thicken this a little bit, right? And now instead of gluing an interval over at 2 points, you're gluing a disk along the boundary, keeping these 2 points fixed, so you're going to get a cylinder. Okay? So assume that the cylinder that you're going to get is bi-infinite. So as you get a Riemann surface, right? You get this thing, call it C mod FQN assume that this is C mod Z. Right? Conformally equivalent to C mod Z. That's easy to arrange. Yeah, just a local thing about how you pick this curve near this point. You can always do that. Okay, what's the upshot of this? And the upshot of this is this really simple observation that C mod Z as an analytic manifold is the same as C mod Z as an affine manifold. By Liouville's theorem, there are no non-affine analytic homeomorphisms of this guy. Right? So this is your canonical affine structure. This is your change of coordinates. This is how you glue. This, if you now look at map G here, so this is defined on a subdomain of this. In particular, it's defined on the circle. Right? Maybe I should draw the cylinder. This is the cylinder. The circle is in the middle. Your map G is defined in some neighborhood. And this is an honest critical circle map. Okay? And that's how I proved the hyperbolicity, in fact, in full generality some time ago.
Where is F defined nowadays?
Huh?
Where is F defined?
F is analytic, so it's defined in some neighborhood of the... Some neighborhood.
What is a fixed point?
So there is a thing called complex a priori bounds, which I proved at some point, which in particular tells you that yes, that this is always true. Any irrational rotation number, you renormalize enough times and you will have this. You will have a large enough neighborhood. In fact, you will have an annulus of a universal modulus, regardless of the rotation number. Doesn't matter what it is. The modulus is always the same, and you will have this picture sitting inside the annulus. Okay? So yes. Okay, so my problem was, so now I should start making reference. So we worked on these questions with Denis Gaydashev from Uppsala. And the problem was that it's hard to generalize this magic to 2 dimensions. Okay, this is not, I don't want to say impossible. Anything is possible. But this is not an easy route to take. So it led us to revisit the basics and go back to this picture, to the business with the gluing and so on. And to redefine renormalization yet again. Oh yeah, by the way, Siegel this, I completely forgot about them. Ooh, shame on me. That's really easy. This picture, right? It doesn't have to be real symmetric. It's the same deal. I mean, here is your Siegel disk. Here is your fixed point. Here is your other fixed point. This is your cylinder. This is the new cylinder. This is, you exponentiate this becomes C star. You fill in the 0, you get, so this is your new Siegel disk. This is your new Siegel disk. And the new map. And this is, I called it cylinder renormalization, right? So this is R sub sil. And this is the same. Okay. You could do this in both cases. Right, so once you talk about cylinder renormalizations, you see that the problem for Siegel and this and the problem for circle maps are not just analogous. I mean, it was clear that there was analogy since the work of Kurt on Siegel this. But this is actually the same. It's the same operator, just different fixed points. Okay, so what were we to do? So let's talk about the problems again. So finite smoothness good because you get a Banach manifold, right? You get C3 and everything is good. And in fact, renormalization will keep C3 invariant. It's just not going to be a smooth operator. And as Valentin told you, On C3 is enough to have convergence, to have fixed point, right? Topologically, you kind of have this picture. But you don't have the smoothness. Now, analytic, on the other hand, is good for R. R will be analytic, but it's bad for the definition of commuting pairs. So the solution, as some of you may have figured out, is to look at the following space. You look at pairs zeta, eta xi, which satisfy the following two conditions. One, eta and xi are analytic. Two, the pair eta and xi is a C3 commuting pair. So what does that mean? That means that I only want to have C3 extensions to a neighborhood of 0 for these two analytic maps, which commute. This is a manifold, right? We call these almost commuting pairs.
Real analytic maps.
Uniform norm. So it's a subset of a Cartesian product of two Banach manifolds of analytic maps. So you have two neighborhoods. I mean, I'm obviously skipping the details, but the details are quite easy. You have to pick two neighborhoods, which will be given to you uniformly by complex a priori bounds, on which these two maps are defined. The norm is the uniform norm, and the commutation condition is a C3 condition. And in fact, you could see, it's easy to check, I mean, trivial in one direction, easy in the other. It's easy to check that the commutation condition is equivalent to saying that the commutator of these two, so eta composed with psi minus psi composed with eta, vanishes at 0 to third order. Okay? All right, so let me start stating theorems. So this is a new setting, if you like, to consider renormalization of circle maps. And you know, we thought it was new for Siegel disk too. And then we discovered that it had appeared in the literature. So for Siegel disk, the commutation, so for Siegel, the critical point is quadratic rather than cubic. So the commutation is the second order. Otherwise, everything is the same, right? So eta composed with psi minus psi composed with eta is O small of z squared. And this was actually considered by Sternemann and Burbanks. Well, one was an advisor and the other was a student. I don't know which is which. But they did numerics in the early 1990s with pairs with this commutation condition. 15, yeah, I know. I'm watching. And saw for Siegel disk, saw numerically saw hyperbolicity. Okay, so let me state some theorems. So these are all joined with Dennis. So let me see. So for circle maps, so Gaydashev, hyperbolicity of renormalization for circle maps of bounded type. So this picture, but with the full horseshoe for bounded type. Okay, and this is not, I mean, this generalizes my previous results because it's a much larger space, right? I mean, this is almost a square of that. It's a much larger space, and well, of course, since the space is larger, it becomes much harder to prove something like this. But however, this is a theorem, And another theorem also with Dennis, hyperbolicity for Siegel with rho equal to rho star. And the reason we fix the golden mean, so there just for the fixed point, and the reason we fix this is because the second proof is computer assisted. Okay? So those in the business who know that this is good for other reasons. So this is like work of Mitsu with Hiroaki Ino on rotation numbers which are close to parabolic. This gives you another group of nicely tractable examples from which to build, positive measure, non-computability, etc., etc. Now starting with continued fraction with a lot of ones rather than a lot of large ones. Okay, so now I have to translate this into answers to the first two questions. So the theorem, the meta theorem, is always the same. Okay, yeah, by the way, it should be evident, right, that there should be no problem extending this definition of renormalization to two-dimensional maps, right, to C2. I mean, this definition of renormalization is just commuting pairs. Take an iterate and rescale. So it's straightforward to extend this to two-dimensional maps. So now this picture doesn't sit in the Banach manifold of one-dimensional maps. This sits in the Banach manifold of dissipative two-dimensional maps, right? Just like De Carvalho, Martins, Lubitsch, and before that, Koch, Ekman, and Epstein, and so on. So the meta theorem is this. If you sit in here, in the stable manifold, then you have a critical circle. So two theorems. First, Gaydashev and me for circle maps. If F is in the stable manifold of the horseshoe, then lambda is a critical circle. Okay? So you'll have, it's going to be a quasi-circle. The conjugacy is going to be, to rotation is going to be quasi-symmetric, but it won't be smooth. Well, it can't be smooth for obvious reasons. Renormalizations converge geometrically fast to something with a critical point on the circle. And the second one for Siegel disk. So critical meaning that the conjugacy is not smooth. It's also critical in the sense that this is a hyperplane, hypersurface. So if you think of my previous picture, this is a codimension 1 submanifold which separates smooth circles from non-existence of the circle. So it's critical in that sense, in the sense of transition. And the theorem for Siegel disk, and this is a joint work with Remus Radu, who is present in the audience and is also is at the institute, and this is about Siegel disk. And this is a conditional statement, if you like, so it will be more general. If ρ is of bounded type and F is in the stable manifold of the horseshoe, then the boundary of the Siegel disk is a circle. Again, a quasi-circle, right? So that biholomorphically embedded disk has a circle as a boundary. And finally, the last bit that I owe you is to tell you that an R with a semi-Siegel fixed point is in the stable manifold. Okay? And why? That is actually easy to understand. Because it's a small perturbation of a quadratic polynomial, right? And the quadratic polynomial is here. And if you take your Hénon family and you just parameterize it by, say, the multiplier, it has to go through transversally, and it will be C1 close to the quadratic family, which also goes through transversely. So it must intersect. And of course, if it intersects, you read off the rotation number from renormalization sequence of periods of renormalization, so it's that. Okay, so that's a theorem for Hénon. So it's a theorem. So to be precise, it gives you a theorem that this is a circle, 4 is a circle, for rho is equal to the golden mean. This is an unconditional theorem. And it's a conditional theorem, conditional on proving this, for bounded type. Right? So we proved the conditional theorem with Remus for bounded type, but the general, but the hyperbolicity statement so far we only know for the golden mean. Now, I wish I had another few minutes to tell you how one could possibly prove such a statement starting from hyperbolicity of renormalization, but Marco wouldn't let me, so I'll stop.
Do you have any idea whether this circle that you illustrated?
Oh, come on, can't you be nice and ask me first to prove that? I'll answer your second question too. But couldn't you just...
Whether that circle
Can't help it, huh?
has a stable manifold, and if so, what the stable manifold is like. It would be the boundary of the Siegel
Cylinder, right. So no, we discussed this extensively with Remus, and we don't have so far an understanding of that. Okay? So any other questions?
How do you prove that?
Thank you, Arcel. Fine. It won't take long. Look, trust me. What? It's out of his hands now. It's questions. Okay, look. So let's say we are on the stable manifold, on this stable manifold, and we are a two-dimensional map, right? So two-dimensional dissipative Hénon. But we are on the stable manifold of a one-dimensional thing. For the one-dimensional thing, what do you have? These are pairs, right? So you have pink disk, some blue disk, 0 is in here, and you have a map defined on the blue, a map defined on the pink, which shuffle these around. And then you can renormalize and so on. What do you have for Hénon? Well, you have something very much like this if you project down to the first coordinate. What you should think of this board is a view from above, right? And you have to thicken this by multiplying by a small disk. Now you can renormalize this. Let me not do raw star. That's not interesting because you get two disks in one and nothing in the other. Let me take some higher period rotation numbers. So you have a bunch. I mean, these are your disks of the next level. They have to live in the previous picture. And what do you know? And again, these are really polar disks. These are thick. And what do you know? You can renormalize. I mean, this is on the stable manifold of renormalization fixed point, so the first renormalization is defined. What's the first renormalization? It means you take this guy, you iterate it a bunch of times until it returns. And you take this guy and you iterate it a bunch of times until it returns. Again, this is not the golden mean. There you iterate fewer times. And you can do it again, right? So you have even smaller disk here, and again, each one of these you can iterate a bunch of times until it returns. But you iterate them by this large iterate. So you could continue this chain all the way. And you see the point is, on the one hand, everything is renormalizable, infinitely renormalizable on the stable manifold. So all these disks are nested. You never actually, these polar disks are nested. You never get out of the previous chain. Secondly, the things at around 0. 0, by the way, is not invariant by our two-dimensional renormalization, in case you're wondering. It's close there, but it's not a fixed point for the rescaling. near zero, they're the same. They're just scaled copies of each other. If you rescale them right, they converge to the same pair of domains. And these guys are essentially one-dimensional pullbacks. So they're all bounded distortion preimages. And where is your boundary of the Siegel disk? Here, in the intersection. And how do you know it's a circle? Well, you just build the conjugacy to the irrational rotation. You just do it brick by brick. You know, you take this partition for the irrational rotation, then you keep refining it. And it works because you're in the stable manifold. You can continue this forever. Okay, that's it. Thank you, Araceli.
Just a small comment. I mean, the fact that this feature here of equability works beyond one dimension did not actually include dynamical. Which was a very important point.
Okay.
They just looked at endomorphism. I think the first place where it appeared was in the paper with Sebastian and Jean-Marc Zambozo. Why I mentioned this paper is because it hints at something which might be much more important, which is that perhaps the reason why we have not yet proved this C2 closing lemma, we don't know enough yet about renormalization.
Okay, thanks very much. I'm sorry for not giving the correct attribution. In fact, I have to say I'm a newcomer to two variables. A lot more room there somehow. So thank you for the correction. And definitely we don't know enough about renormalization. Yes. Carsten, you had a question.
So what do you say if you have two or more critical points?
On the circle?
On the circle, yeah.
On the circle, you could say
Anything you want?
you could say the same things, but in a more complicated fashion. I mean, things start to become combinatorially complicated, right? And in combinatorially easy cases, one of the points will just go out of existence, and you'll be left to renormalize around the other. But in serious cases, somehow both points will be in play. So I'm not sure if there are any papers on circle maps. I mean, I know Jun Hu, for instance, worked on this for unimodal maps. And I know other people did too. But I don't know about the circle maps. I don't know if there are papers on that. Smania worked on this for unimodal maps, yeah.
Student of Edson. Yeah, Edson as a student.
Who's working on several. Yeah, so Carsten, so the complications that you get are at the combinatorial level, not really at the level. So most of the theory carries through complex bounds, two critical points, even better, right? Real bounds the same, so the thing is...
Complex bounds. This discussion is becoming...
Yeah, sorry, Marco, you're right. I'm just trying to annoy you, sorry. Yeah, thank you.